So not just make squeeze states of light, but really make squeeze states of the mechanical oscillator itself, so that you don't even have the problem of contending with the vacuum fluctuation of that object. And then you can think of doing things like tests of macroscopic decoherence and things like that. I think I would actually leave it at that. I do have some slides for slides that cover how this could potentially be done, but I think I'll stop there. Thanks. I'm happy to take questions. We are not actually there yet. So we actually see the 0-point motion of the mechanical oscillator. So it's a good question because I do have a slide on it and I skipped the slide. So, so where's the 0-point motion of the mechanical oscillator? And we do see it. So okay, so we go back here, which is what I skipped. So I told you that there are these correlations between the amplitude and phase of the mechanical oscillator. So what you can do is instead of subjecting the light to a homodyne measurement, you can think of subjecting it to a heterodyne measurement. So you take the light coming out, beat it with a frequency shifted local oscillator and do photo detection on that. Turns out as you cool the mechanical oscillator, so you can think of the mechanical oscillator as just a Raman scatterer, right? So light bounces off and then it creates two sidebands. So it's the upper sideband, lower sideband, and one of them is proportional to the mechanical oscillator getting de-excited, the other is proportional to the mechanical oscillator getting excited. Of course, if the mechanical oscillator is close to its ground state, its ability to de-excite becomes zero, right? So as it gets closer to the ground state, it sort of cannot de-excite, but it can excite, because the ground state is sort of the vacuum. So as you do this, what you should see, as you cool the oscillator further, what you should see is that the upper sideband should sort of vanish and the lower sideband should sort of stay the same, and then the difference between them is simply the size of the 0-point motion in some sense, as it turns out. In fact, it's the magnitude of the mechanical oscillator commutator. And you can actually see that here. So as you cool the mechanical oscillator, you see that the upper sideband and the lower sideband sort of have a relative disparity in their noise power, and the ratio is basically n by n plus 1. Where n is just the total occupation of the mechanical oscillator, and that 1, the asymmetry, is just due to the 0-point motion of the mechanical oscillator, and we see an asymmetry of about 12% corresponding to that basically. So, and that's consistent with the 0-point motion of the mechanical oscillator. Having said that, I should say that when you do heterodyne measurements like this, there's also an alternative interpretation that's equally viable for why this is the case, and in that interpretation, this one comes from the optical commutator and not the mechanical commutator. But this is sort of a general feature of all linear quantum measurements, that you always have an ambiguous interpretation between where the quantum noise comes from, whether it's the measuring device or the system being measured. Sure.
What detectors do you have for 1064?
Oh, there are in commercial in-gas detectors which have much more noisier than
the silicon detectors. They have a lot of noise.
Not necessarily. I mean, LIGO uses in-gas detectors. No, these are not cooled. These are room temperature detectors. So there is a difference between single photon counting detectors and continuous wave detectors, continuous wave photo detectors, I would say. So single photon counting detectors are sort of, they directly measure the normally ordered A-dagger ray of the field. Whereas these photo detectors sort of don't do that. They sort of measure fluctuations about a large carrier, so there's no normal ordering involved, which is part of the reason. But the point is that by simply increasing the optical power falling on these detectors, you can more or less overwhelm the Johnson noise of the detector. So that's practically the thing. And in LIGO, optical power is not a problem. That's a plenty. So.
Now it's time to share again.